a perfect circle of glowing mushrooms standing out in the dark grass. This formation, known as a fairy ring, follows a strict geometric logic. The mushrooms visible above ground are temporary fruiting bodies, representing only a small fraction of the total organism. Below the soil lies the primary structure, a vast, invisible fungal network known as mycelium. Mycelium consists of a mass of branching, thread-like fibers that expand outward from a single central origin point to forage for nutrients. The surface ring serves as a biological footprint, mapping the exact outer boundary of this underground expansion. To maximize nutrient intake, the network grows radially, pushing away from the center in all directions simultaneously. Uniform expansion from a central point naturally generates a circular boundary. We can analyze the mechanics of this growth by building a mathematical model from first principles, beginning with basic algebra to track the ring's expansion. Translating these biological processes into mathematics provides the structural language needed to map growth occurring entirely out of sight. Our initial model assumes the fungus begins at a solitary point of organic matter and spreads outward at a perfectly uniform rate. As the mycelium expands, mushrooms only emerge at the absolute outer edge, where active growth and reproduction occur. The distance from the underground central origin to this active mushroom edge is the radius, r. In geometry, the radius is the distance from the center of a circle to any point on its perimeter. Because the growth rate is uniform, the length of this radius remains identical at any point 360 degrees around the origin. By tracking this single one-dimensional vector over time, we can predict the entire geometric footprint of the organism. To turn this observation into a functional model, we map how the radius expands over time. We define t as time and r0 as the starting radius length of the organism. We define k as the constant, uniform outward growth rate, the physical distance the fungus covers per unit of time. Combining these variables yields the fundamental linear equation for the system. R of t equals r0 plus k times t. This function dictates that the active biological edge moves away from the center by a constant mathematical amount every month. For a uniform biological system, simple linear algebra is a sufficient tool to map the perimeter. Next, we must account for dimensional scaling by comparing the growing edge to the total ground the fungus consumes. This chart shows the circumference, the active ring edge, modeled by the formula 2 pi r. Because the radius grows linearly, the circumference also scales at a steady linear rate. However, the total internal area consumed by the network follows a different scaling law. The area is modeled by the formula pi r squared. Because area is tied to the square of the radius, it grows quadratically, accelerating as the ring expands. This creates a biological cost. To maintain a steady linear expansion at the edge, the total network must consume quadratically more resources from the soil. The tension between linear perimeter growth and quadratic area consumption defines the physical survival limits of the organism. Our model requires one final refinement. The mushrooms don't cover the full quadratic area. They only populate a narrow perimeter band, leaving the interior empty. We define this shape as an annulus, the region bounded by two concentric circles. We assign r as the outer radius and w as the width of the active mushroom band. To find its area, we take the total area, pi r squared, and subtract the inactive inner void, which is pi times the quantity r minus w squared. Simplifying that algebra yields a precise formula for the active reproductive zone. The area of the ring equals pi times the quantity 2rw minus w squared. This formula provides an exact footprint of the active biological zone, stripped of the dead space inside the ring. This mathematical model relies on absolute environmental symmetry. In reality, soil is heterogeneous. Variations in moisture, nutrients, and physical barriers like rocks force the network to warp and branch asymmetrically. These obstacles disrupt the uniform radial expansion that our simple model assumes. When the environment is uneven, the constant growth rate, k, no longer accurately describes the entire system. Perfectly symmetrical algebra cannot account for the unpredictable variations of a real ecosystem. Modeling this asymmetric biology requires moving beyond algebra into calculus. Researchers must calculate the instantaneous rate of change for multiple points along the ring. We label this dr over dt. In calculus, this derivative represents the rate at which the radius changes at a specific moment in time. Differential equations are then used to map this non-uniform growth across an entire environmental field. Basic mathematical models provide the necessary scaffolding for these more complex descriptions of nature. From simple linear growth to the complexities of differential equations, these mathematical tools allow us to quantify and predict the physical boundaries of life.